Welcome to lesson 15. In this lesson, we're really going to deal a lot with radicals. And the reality is that radicals are rather unpredictable. Sometimes they just do things that we're not expecting. They can cause a lot of side reactions. Or they could just not work on a particular day. At least not the way that you're wanting to. If you want to consider what a free radical is, a free radical is essentially an oxidant. So all those antioxidants you're pumping through your body are there to get rid of radicals, because radicals, as you know, as a free electron, they're radically trying to find a partner. And so that means that they'll rip through your body and do a lot of damage and cause aging and things like that. They've been linked to aging at least. So when we're dealing with radical reactions, you just have to be really careful when you're doing these in the lab. Let's start with some things that really you've seen, actually all of this, except for one little tie-in in Orgo 1. If you start with an alkene and you add HBr, you're going to get a Markovnikov product. I'll go through the mechanism for that in a minute. Markovnikov because it's on the most substituted carbon right there. But if you do the same reaction in the presence of H2O2, which is a radical initiator, UV light or heat, then actually what we end up with is an anti-Markovnikov addition of Br. Same alkene with Br2 will give you a dibromo product. But once you add H2O2 with a radical initiator, you actually get a bromine at the allylic position. That relates to something that we've already talked about, and that's a something out of nothing reaction, which I'm going to go over yet again. So this is sort of what we're building to. We've seen these three in Orgo 1 already. This is what we've got to discuss today. NBS is something, N-bromosuccinimide, is the same, we just call it NBS because it's easier to write than that crazy word, but that's basically going to form Br2 in situ. In situ means that it's going to form it inside the beaker, and the reason why we want that is that bromine is kind of a nasty chemical by itself. You don't want to get it around you too much, partially because it does create radicals. But you know sort of what chlorine gas has done in our past, so bromine's kind of nasty like that too. So if you look at different types of radicals, the ones that are most stable are the ones that form the most resonance structures like everything else. So that means that benzylic and allylic, they're about the same. Benzylic is a little bit more stable. Tertiary, secondary, primary radicals, so it goes in that order of stability. Vinylic, or just a methane radical, those guys are very unstable, so they're sort of in the same category. Okay, so let's start looking at these mechanisms. As you've seen in Orgo 1, an alkene bond with HBr, this guy comes and grabs that. You end up with a positive charge here because the hydrogen went over here, because that positive charge is most stable on a secondary carbon versus a primary. So that means that the bromine comes in here, and you get a Markovnikov product. Well, in a radical reaction, what we find is actually that you get an anti-Markovnikov product, such as this. Okay. And I flipped this around just a little bit, so it is backwards. My apologies, I just realized that. But what I'm trying to show, this Br actually comes from over here on this side, okay? It does that because note in this step right here, and I know I haven't even talked about these yet, but note in this step right here, we have carbon, 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 and we've got a radical on the most substituted carbon. The same way that up here we have a positive charge on the most substituted carbon. Each of these are stabilized by being on the most substituted carbon, and that's why these reactions happen the way they do. Okay, so let's go back. When we're talking about a radical reaction, it goes through a series of reactions. And you have to really think about what is it that's in this beaker. And you have to think about a population of molecules. So let's say that we start off with hydrogen peroxide. We use UV light or heat and we break that apart, which is why, by the way, you don't really want to be around concentrated hydrogen peroxide in heat because it will kind of blow up and it starts burning and it won't stop. So once you have a radical, which is not easy to make, that's another reason why too your hydrogen peroxide comes in a brown bottle when you buy it at the store. But let's say we have this radical here. You purposely put in a whole bunch of this HBr. And remember, fish hooks mean that only one electron is moving. So we've got this HBr bond right here is being split up. One electron is going there, another one's going to that bromine. So you make an alcohol, great, that becomes part of the solvent. Then you make this guy. You might make 1 or 5 of him in the entire solution. But he's now going to go and play the game of wreaking havoc. So here he goes. He's going to come and, man, I found something to wreak havoc with. And so what happens is these electrons come in, it forms this new bond. This bromine chooses to go to the least substituted carbon because that means that the radical will be on the most substituted carbon. Once you have him and another HBr, they come together, your H comes here, and guess what? You make another Br radical. This happens over and over and over again. Because as I said, you might have like 5 of these guys in the entire solution. But you've got like millions, billions, beyond trillions of these. Depends on how much you put in, obviously. But we've got a whole bunch of this. We've got a whole ton of this, too. So instead of finding another Br radical, that's pretty rare. That would stop the radical reaction if that were to even happen. But instead, there's tons of these around, and that's the reason why they actually would go and react. Okay? And so what happens is once you get this Br radical back out, it comes right back here, and it repeats this process over and over again. It just keeps going through that. Okay? Until essentially your fuel source, if you will, this guy is spent. In other words, you don't have any of that left. Then, basically the reaction starts to finalize itself. And the reaction terminates. And it terminates by having 2 radicals that find each other. See how that makes almost a little heart there? Oh, they found each other. They find each other. They find each other. And yes, you end up with a very minor amount of each of these. But it's very minor in comparison to up here. Radical lifetimes are so short that they just don't last long. So, in truth, you could have 100,000 of these happen very, very quickly. It's another reason why it's hard to control. Okay. Now let's move on to the next type of reaction, if I can get this. There we go. We've already seen in Orgo 1 that Br2 in an alkene goes and makes a bromonium ion, you see right here. Bromine comes in here and attacks, that leaves, and these guys end up trans. Because this can't attack in the same place that that is, so they end up being trans. Well, it's a little bit different than that when you're dealing with the hydrogen peroxide and either, some type of radical initiator, either light or heat. Before I talk about this, though, I want to talk about one of my favorite reactions, and that's the make something out of nothing reaction. And here's what I mean by the make something out of nothing reaction. Here we've got a cyclohexane, methyl cyclohexane, Br2 and light. What we end up with, we end up with the Br right here, H2O2. Nah, we could do it with just light. That'll work. Okay, there we go. So in this case, what we're doing If you see this with H2O2, it's totally the same thing. The H2O2 is just ending up making a radical easier, okay, easier to make. It would be a radical initiator in this case. So in this case, once you add light to Br2, you make 2 radicals. That's your initiation process. Then we come down here, right here. Of all the hydrogens that are available in this particular molecule, this bromine is going to choose that one. And the reason why it does that is this is the most stable radical intermediate that can be formed. Once it chooses a radical, then it comes over and says, okay, well there's my Br2. I'm going to combine with him. He's going to go away. And bam. So your bromine ends up on the most stable location for a radical to be, or the most stable place for really a carbocation to be. Most substituted carbon is the easiest way to say it. That bromine radical then again, it goes over and over and over and over. And again, to terminate this reaction, 2 radicals have to find each other. Okay, so we get Br2, we get Br here, or whatever craziness you have there. Okay, so let's go back and talk about this radical stability. If it's the case that you're trying to make the most stable radical first, and that's where the bromine adds, well, guess what? These 2 guys right here are more stable than any of these, right? So if you could actually have a case where the bromine is exposed in H2O2, a radical initiator, then this is where the most stable radical will form. And that's exactly where bromine goes. That's the end. See, it's not so difficult. Don't overcomplicate this. Don't overthink it. You can actually reason your way through these mechanisms. So the first thing that I would say is forget about the termination. Make your radical, and then think about what's the minor thing that I have in the solution, what's the major thing. Each case you're going to get a bromine radical in the end. Then that's what goes through this process. The termination is actually really easy. Go and look up at what you did above and say, okay, well, I need 2 radicals to come together. So, okay, I can have this one and this one. I can have 2 of these. I can have this one and this one. See how that's really the same thing? Just an easier way to study. Same thing with the other type of mechanism. Nope. 2 of these coming together, 2 of these coming together, bam, bam. And those are what your termination steps would be. These are really fun to use in synthesis too. At least fun for me. Thank you.